if you have the opportunity to visit Côte d'Azur, our university is called Université Nice, Sophia, Antipolis, and now we made it into a new university which is called Université Côte d'Azur. So please take the chance and visit our lab and our campus Park Valrose. So we work on Rosetta, and before presenting you our data from the Rosetta mission and the organic identification of Philae, the Rosetta lander, I would like to explain you what we expected from landing on a comet, from which molecules we wanted to identify. So we simulate comets in the lab. We produce artificial cometary ices. And we use, therefore, the Greenberg model, which you see here. You have here these IDPs. You have volatile molecules like carbon dioxide, carbon monoxide, water, methanol, and other structures. These molecules condense on the surface of these particles. They form layers. During condensation, they are irradiated by interstellar radiation, and then some photochemistry occurs. So we would like to know what's going on there, so we reproduce these processes in the lab. Here is a chamber. We use high vacuum. We use very low temperatures at this support material, which you can see here, which is at about 12 Kelvin, minus 261 degrees Celsius. We condense molecules like water, carbon monoxide, carbon dioxide. You have seen these molecules before. Please recognize that all of these molecules do not contain any preformed carbon-carbon bond or carbon-nitrogen bond. So we talk about N1 units and C1 units. We condense them at low temperature, and during condensation on the surface, they are irradiated, in this case with Lyman alpha. Here's the experimental setup. And what was published before, that many different amino acids form in these artificial cometary ices. 16 different ones were detected, like sarcosine, for example, alanine. And for the specialists among you, we detect alanine in a racemic ratio. D-alanine and L-alanine in 50-50 ratio. So these molecules are not contaminants. They were generated by these C1 and N1 ingredients. In order to be sure that these molecules were photochemically produced under simulated interstellar conditions from these C1 and N1 units, we reproduced the entire experiment a second time prior to publication. And in the second experiment, we employed the carbon-13 isotopes. We again produced 16 amino acids, and in this experiment, you see for each amino acid a mass shift that corresponds to the number of carbon atoms per amino acid. And according to this mass shift, we can be sure that all of the 16 amino acids that were produced contain carbon-13 isotopes by 100%, and as a consequence, they were indeed produced by the C1 and N1 units introduced into the system. This was published many years ago. Since then, we changed our analytical procedure, and today we use something which is called multidimensional gas chromatography. This means we have a first capillary column in which we separate our organic molecules, such as amino acids. These molecules, after their first separation, enter into something which is called a modulator, from which they are injected into a second capillary column from where they are detected. So in multidimensional gas chromatography, we have one injector and one detector. The first dimension of the capillary column with its stationary phase is connected by a modulator to a second capillary column. And in the modulator, there are phenomena that occur. We have cold jets, we have hot jets, etc. So what can it do? You have here this separation, this bad separation, one-dimensional classical separation of three analytes that are called alpha, beta, and gamma. And they are not well separated, as you see here. They're not baseline separated. We use now multidimensional chromatography, and we can well resolve on two dimensions now alpha from beta and beta from gamma. And this is what we obtained in our lab. This is a standard of amino acids, of a mixture of different amino acids, analyzed by multidimensional gas chromatography. Some of you may spot that we have double signals here, and these double signals correspond to no isotopes. No. We use gas chromatography. So, should I say it again? Should I start from zero? No. Yes?
Are these optical isomers?
Exactly. These are optical isomers. We call them enantiomers, D enantiomers and L enantiomers, because we use a chiral stationary phase. So this is a standard, and this is now a sample of our artificial cometary ice. Today we see 30 different amino acids in these cometary ice, and here you see some of them that are resolved in 2 dimensions. Those amino acids that you see here, we consider them as particularly interesting for processes considered important in chemical evolution, and we call these amino acids diamino acids. These amino acids contain 2 amino groups and 1 carboxylic group, and as a consequence we call them diamino acids. We are very much interested in the chirality of those amino acids, and therefore we try now to better reproduce interstellar conditions from where we know that photons can be circularly polarized. We talk about chiral photons in star-forming regions, for example, of Orion. So now we try to reproduce these ices, artificial cometary ices, by using circularly polarized light, which can be right circularly polarized or left circularly polarized. We talk about chiral photons. So this property of chirality, we do not know only for molecules or for electrons, also for photons that can be chiral. We try now to transfer, as it occurs, as a hypothesis under interstellar conditions, we try to transfer the chirality of photons to the chirality of the amino acids that were produced. So what you see here is the experimental setup. This is our synchrotron center. We have an undulator. We produce circularly polarized synchrotron radiation at different energies. We use different filters. We use a grating to select an energy. We can measure the circular polarization by using a polarimeter. And here, this you know already, this is our surface. At cryogenic temperatures, we deposit these molecules, water, ammonia, and carbon-13, isotopically labeled methanol, and we again produce from this C1 and N1 units many different amino acids. Most of them are chiral, and as you can see here, in this experiment we irradiated with left circularly polarized light, so we can say with left chiral photons, and we produced an excess of the L enantiomer of the amino acid. Here we irradiated with non-polarized light, and here we irradiated with right circularly polarized light. So you learn, yes, it works. We can introduce an enantiomic excess of about 5% into amino acids by using chiral photons as they occur under interstellar conditions. We then continue the analysis of these artificial cometary ices and now published the formation of ribose in the ice. So we do see ribose, arabinose, luxose, xylose. We see many different aldopentoses and aldohexoses as you see them here. Ribose, arabinose, xylose, luxose, ribulose, xylulose, and many different ones. We see aldoses, we see ketoses, and the beauty of this is that we assume to know the formation mechanism of these aldopentoses in the interstellar ice. These ribose molecules that formed have never seen the liquid phase, liquid water. We assume a formose reaction that occurs in the condensed solid state. And this formose reaction involves the condensation of 2 molecules. This you can call the C1 units, which are formaldehyde, that form out of the other C1 units that we had introduced into the system. So we have 2 formaldehyde molecules which condense to form glycolaldehyde. And what is important here for the chemists among you, this reaction number 1 is catalyzed by this molecule. And as you can see, this molecule is identical to the product. So we do not only call this a catalysis, we call this a autocatalysis, exactly. So the product, glycolaldehyde, forms, it catalyzes its own production. And this is very important, a very important result. Then it continues with another C1 unit, which is formaldehyde, to give you glyceraldehyde, and then you get the ribose, for example, here, and you get other sugars here. So there we try to link astrochemistry with astrobiology, because we have maybe the first autocatalytic cycle under this very simple, pristine conditions in the condensed solid phase. So this is what we wanted to detect with Rosetta. This is the Rosetta orbiter. You have seen that already. Here you have the Philae lander implemented onto the orbiter. Here's the Philae lander on the orbiter. This is Churyumov Gerasimenko. You can see this Hathor. You can see the neck region. You can see the big lobe here. These very beautiful images that were obtained in November in 2014, 2015. Please allow me, my family name is rather complicated, so I put my family name of each of these slides. Sorry for that. On the next slide you see my family name and also my first name, which is this one here, Uwe. The reason for that is that you can see already Uwe, U, W, and with a little bit of imagination you can see the E, which is on the comet. Emote. Emotape region. So we were involved in this Rosetta lander called Philae. I don't have the time now to go into details. This was on November 12, 2014, the landing. First image of the Philae lander taken from Rosetta orbiter after separation. This is an image taken from Philae lander, and here you see the Rosetta orbiter after separation. This is a sequence that Philae lander turned around the z-axis during descent of 20 kilometer distance. Then an image taken from Rowley's camera. Here you see one of the feet of the Rosetta lander and the comet approaching directly prior to landing. This is an image from the Rowley's camera of the landing zone. The big image is taken from the Rosetta orbiter. Champagne was served in Cologne. François Hollande was at Cité de la Science in Paris. He gave a talk, science is beautiful and science needs to be international between France and Germany and many other countries and Europe and the United States. And this is a beautiful endeavor, and only this can be done by international scientific collaboration. And we saw that image from the SIVA cameras of the Rosetta orbiter. This was before, this was after. You take the difference and you see the 3 dots on the cometary surface, but the Philae lander is missing. So it was hopping for about 2 hours. This was then an image taken after the final landing. On Wednesday, November 12, 2014. This is how it's supposed to be located there. This was a special issue in Science. And in the Philae lander implemented is our COSAC instrument, which is a gas chromatograph coupled to a mass spectrometer. And you remember gas chromatography coupled to mass spectrometry is the same technique that we used for the identification of all these 30 different amino acids in the artificial cometary ice, of ribose in the artificial cometary ice, and we also found 10 different aldehydes in the artificial cometary ice. So we use the same technique, gas chromatography coupled to mass spectrometry. So here you have a drill, which is not depicted, giving us a sample. Here you have a carousel, 24 ovens. The cometary sample is supposed to be filled in these ovens. They are transported on the carousel into the tapping station where they are closed and heated. And the volatile molecules you get by this transfer line into this gas chromatograph of COSAC, the cometary sample and composition experiment. And from there you have another transfer line that transports the separated organic molecules into our time-of-flight mass spectrometer that you see here. These are the gas tanks of the helium carrier gas. And here's an image of the flight model of COSAC. Then Friday, after having been nearly 60 hours on the comet, the batteries were supposed to run empty, but we were very lucky to have obtained many mass spectra after the final landing event on Friday, 14 November. We obtained 427 mass spectra. And this was the line of the battery. Here it ran empty. It was empty Friday night at about 1 o'clock. We obtained all these spectra Friday night at 11 o'clock. So 1 or 2 hours before the batteries ran empty, after 60 hours of operation, after landing on the cometary nucleus, the primary batteries ran empty, and we obtained many of our data 1 hour before. So we were very lucky to have all these 427 mass spectra. Add to this, we measured in the automatic sequence 20 minutes after the first touchdown on the comet, which was on Wednesday, cometary material that we supposed that have entered here into some exhaust tubes in between the GC and the mass spec of the instrument. Here you see them again. The inner diameter is nearly 20 millimeter. We suppose that cometary material entered here, cometary dust grains, cometary ices, cometary volatiles. And in this zone, this material has seen for the first time something like 300 K room temperature. So these molecules, the volatile molecules, sublimated and entered directly into the ionization source of the mass spectrometer. What was recorded then on 12 November, Wednesday, was this mass spectrum. This was recorded 2 days thereafter, and this was recorded before. So you can see in this mass spectrum that was recorded before, some noise and 3 signals. One signal is at mass of 18 m over z. What is that? We have a second one at 28. What is that?
Nitrogen.
And 44?
CO2.
Perfect. Perfect. So then we have this spectrum, which was measured on Wednesday. And here you see the black is the spectrum that we measured, and in orange we try to calculate a fit of a mixture of organic molecules to obtain the black spectrum. And for this calculation we required 16 different molecules. These 16 different molecules are again depicted here. We have water, carbon monoxide, methane, we have all these molecules, alcohols, carbonyls, amines, so nitrogen molecules, we have lots of aldehydes, carbonyls, etc. So these 16 molecules were required to reconstruct the fit of the mass spectrum 20 minutes after the first touchdown of the Philae instrument. The next question is, how do our simulations of the cometary ices relate to what we measured? The techniques were identical. In the simulated ices, we detected amino acids, aldehydes, aldopentoses, including ribose and other sugars. In these ices, we see aldehydes. We do see ethanol, which is acetaldehyde. We do see propanol, which is propione aldehyde. And we do see this one here, hydroxyethanol, which is glycolaldehyde. And these aldehydes we also see in the simulated ice in high quantities. In the real comet, in this sample, we do not see amino acids. We do not see aldopentoses, including ribose. Why not? Because amino acids and ribose are called refractory molecules. And as I try to explain you the way of this measurement, we measured just those molecules that sublimated to enter into the gas phase. We were only able to detect volatile molecules because we used this what we call sniffing mode of the Kozak instrument. Right. And this is the reason why we did not detect aldehydes, why we did not detect amino acids and ribose by Kozak on board Philae. I am convinced that amino acids and sugars such as ribose are present in the cometary ice, but we did not see them because we only used the mass spec instrument. If you're interested on this, I wrote a book on chirality, which is this one, and another one on comets, which you see here. Many people helped in this scientific endeavor, and here are some sponsors. I would like to thank them, and I would like to thank you for your kind attention.